All right, so we'll say this again. On Thursday, we have a quiz, 6.3, problems 1 through 9, 7.1, 1 through 4. And then we skip 4 sections to go to this one. We're going to come back and do this again. Be able to do 1 through 8 out of 7.5, all off of the UCO supplement. And this is a hard section, so bring some questions, and especially on this tomorrow, but on all 3 of those sections. Today, I'm going to skip over, go back and do what I skipped over, which is more identities. There are lots and lots of important trig identities. This will be on the exam that's coming up a week from Thursday. How about that? This is practice for the exam. These things will be on the exam again too. The exam will cover everything since the last exam, all right? And I'll give you a practice exam end of the week. So over this weekend, look for the practice exam and be practicing those for next week. So today we want to look at the sum and difference identities. We gave a list, pretty exhaustive list of everything we covered last time. And we used those to simplify trig equations and to verify new identities. But we can do even more if we just have some more identities, right? The idea is to get such a repertoire of these things that you can, when you see things in your science class, reduce anything you see and verify other identities that you see. So that's the main thrust of this, but there's also some additional things that you'll see today besides those. Some of the difference identities. This has a neat proof in it using the unit circle, but it takes too long and nobody can remember it. I certainly can't remember it. And I have to go back and look it up every time. So I'm just going to put the results of it. And these are the results of the sum of difference identities. That you get a nice proof on the unit circle. It says that this holds. What if you have the sine of the sum of 2 angles, x plus y? So these are 2 different angles. Is there a way we could write that in terms of trig functions of just x and trig functions of just y? And it turns out the answer is yes. On the unit circle, you can show that this is actually equal to the sine of x times the cosine of y plus the cosine of x times the sine of y. They proved that one, and then they derived the other ones from this. And once we have that one, the other ones aren't so hard to get. This gets to be a lot of stuff to remember. So here's how people remember it. The sine of x plus y is sine cosine plus cosine sine. You just say that and put the x and y in the same order. Sine cosine plus cosine sine is the sum rule. All right, so it's called a sum formula, sum identity, because it's for the sine of a sum. Now, having said that, so this is my hand waving proof. I tell you about hand waving proofs. I always tell this to my upper division class. I don't know if I told you that. When something's too long and too complicated to prove, I wave my hands real fast and you just believe it, right? It's like a magician. They do that in science all the time. They don't want to prove this stuff because it's not a math class, and so they dance and wave and you believe them, right? So anyway, that's a hand waving proof is when you don't really prove it. This, however, we can do a real proof of the next one. This holds for any numbers x and y. They can be positive or negative. So what if I replace y by y replace y by minus y, so I'm taking the sine of x minus y. How can I get an identity for that? And this is a useful proof because it's going to be kind of like some of the proofs we do here. I know if I just wrote it as sine of x plus negative y, and this holds for all y, then I could use this identity for the sum, right? This would be sine of this angle, cosine of the other one, plus cosine of the first angle, sine of the second one, right? Sine, cosine plus cosine, sine. I'm using this one that I already proved. So this one's hard in the unit circle, but this one is easier. We'll do it. And so when I'm insightful and short, we'll do it. Partly because this is how I get all this stuff. When I was a student in trigonometry and everything else, what I always liked about math is instead of foreign language where when you couldn't remember it, you just couldn't remember it. Here, if I can't remember, I can figure it out, right? So I'll say cosine of minus y, cosine is an even function, right? the even odd identity, so I'm going to replace cosine minus y with cosine y. And sine is an odd function. The minus comes out and it gives me minus cosine of x, sine of plus y. So by the even odd identities, I can rewrite it like that. And there it is. Here's the identity for the sine of a difference of two angles. I have now sine of x minus y. The difference is sine cosine minus cosine sine. How about that? It's not much harder. So if you remember the first one, you can remember the second one. You just replace the plus with the minus on both of them. Right? Easy. Now you almost remember 2 and 1. That's a little better. So this is the hand waving proof, and this is a proof. If it just came in the quiz on Thursday. 6, 3, 7, 1, and 7, 5, and we're going back to 7, 2 through 7.4. So better yet, let's put these together. Since they look so similar, this is how I remember them. If you have sine of x plus or minus y, it doesn't matter which, then you get sine, cosine, plus or minus, cosine, sine. So once you've seen this proof, the second one's easy to remember than the first. You can figure it out when you forget it. You just have to remember that first one. Sine of x plus y is sine cosine plus cosine sine. Switch these to get the other one. Let's call that equations 1a and 1b. These are the sum and difference formulas for sine. Right? Plus goes with plus, minus goes with minus. Right? You remember them easily. Similarly, and again, I'm going to do a hand waving proof. I should put 5 fingers. Anyway, get tired and draw 4 sometimes. Similarly, waving my hands, I'll say you can get formulas for cosine, and you can actually derive those from the other identities. The cofunction identity, since cosine of an angle is sine of pi over 2 minus that angle, you use the cofunction identity to derive corresponding formulas for cosine. So by using the cofunctions identities, and again, the even odd properties. This one is easy for me to prove, but I think it's not worth your time. You can show that the cosine of the sum of two angles is cosine cosine minus sine sine. And that's the sum of angles identity for cosine that you can derive from these two with a little bit of. And then if you replace plus y with minus y, just like you did in that proof, then you get a minus here. Cosine of minus y becomes cosine of y, so this one stays the same. And sine of minus y, the minus comes out and gives you a plus here. So again, plus with this time, plus goes with minus and minus goes with plus. That's the one thing that's a little harder about this. But again, if you know one of these, then the even odd identities put together. Let's call these equations 2a and 2b. Say these are the sum of different formulas for cosine. Okay? And these do some interesting things for us. This is the whole identities for this section, is these 4 put into 2 very similar things. With these, we actually can finally do some trig functions of different angles than special angles, not a whole lot more, but with these, we can now compute exactly by hand. And your modern calculators can do these, the nice ones, exactly also, since it knows these formulas. The sine and cosine of any angle that's a multiple of 15 degrees. Well, what angle is that? What angle is that in radians? Pi over 6 was 30 degrees, and so this must be pi over 12. So now we've got a whole bunch of new angles, any multiple of 15 degrees. It's not all that many more, but we can do 15, 30, 45, we could already do at 60. We can do 75 and 90 and 105. So all those 15-degree angles in between the special angles, 15, 75, 105, and others, we can now do exactly also. And it's a pretty easy calculation. And we do this by simply rewriting these as a sum or difference, it doesn't matter, of special angles, the ones that are multiples of 30 or 45 degrees. That's the first point. I should put 1 here. So we can do a whole bunch of new angles, all those that are multiples of 15 degrees. Oh, I shouldn't have erased that probably. I'll rewrite it. So here's our sine x plus or minus pi is sine cosine plus or minus cosine sine. That was 1AB. And cosine x plus or minus y is cosine cosine minus or plus sine sine. Well, that's 2AB. Let's do an example here, illustrating what we can do. I always wondered, maybe, we know the sine of 30 degrees and the sine of 45 degrees. What is the sine of 15 degrees? This is what a whole lot of textbooks start off with to illustrate it. So I'll start off with, how can I compute the sine of 15 degrees exactly? If I think of it as a sum or difference in special angles, I could take, let's see, 60 degrees minus 45 degrees and get that, for instance. So let's rewrite that as sine of 60 degrees less 45 degrees, right? These are both special angles, multiples of 30 and 45. So now by equation 1A, excuse me, 1B, since it's a difference, by equation 1B, sine of x minus y, sine cosine minus cosine sine. So if I call this x and I call this y, what I have is sine x cosine y minus cosine x sine y. I have to fill in x equals 60 and y equals 45. So sine 60 cosine 45 minus cosine 60 sine 45. Sine cosine minus cosine sine. And those I know how to do, right? When they're acute angles, angles between 0 and 90 degrees, I'll just look at my special triangle. That's easier than going to the unit circle. So I'll say, here's the 60-degree angle and the triangle that fits with it. You can either put 1/2 square root 3 over 2 and 1, or you can put the 1 square root 3 and 2, whichever one you like to memorize for these. Sometimes the 1 square root 3, 2 avoids your fraction. But we'll say now that sine of 60 degrees, what is it? Well, it's this one over this one. It's square root 3 over 2. And cosine 60 degrees. Well, it's adjacent over hypotenuse. It's 1/2. Oh, I broke all my good chalk. Hold on. I'm losing my fingernails today, I guess. All right. Keep you awake for a change. Now let's try the 45, 45, 90 triangle. That's the other one. This one, we can put square root 2 over 2, square root 2 over 2, 1, or you can put 1, 1, square root 2, whichever one you like on that one. There's the two triangles. So cosine is adjacent over hypotenuse is square root 2 over 2. And sine likewise is square root 2 over 2. There it is. If I just multiply and subtract, I've got the exact calculation. Let's see what it is. It is, top times top over bottom times bottom, right? It's square root 6 is square root 3 times square root 2 over bottom is 4. And the next one, minus 1 times square root 2 is minus square root 2 over 4. And luckily, they both have the same denominator, so I can subtract them directly. It's just square root 6 less square root 2 all over 4. There is the exact value of the sine of 15 degrees. How about that? So sum and difference identities are real nice like that. 15-degree multiples are not all that uncommon, right? That seems reasonable to do. Well, let's try another one. Suppose I wanted to take the cosine of 205 degrees. Sorry, 195 degrees. 195 degrees. Is that an angle I can do now? It is. It's a multiple of 15. Here's how I usually figure out. There's lots of ways to do it. Whether it's a multiple of 15 degrees. If this comes within 15 degrees, a multiple of 15 degrees from one of the coordinate axes, you can do this, right? Like here's 180 degrees. And if I go 15 more, that makes 195. Every coordinate axis is a multiple of 15 degrees. So if I go to this coordinate axis, I'm within 15 degrees of it. Then it's a special angle. So I notice this is only 15 off from 180, so it's special, right? So I'll check. It's not special. It's a multiple of 15 degrees. So this means I can do it. Well, this time it's cosine. So if I consider cosine of, let's do the sum of angles. 180. Oh, 180 plus 15. Why isn't that good? Fifteen isn't a special angle. I'll have to do this formula again to get the cosine of 15 degrees. I want to pick two special angles, but any multiple of 15, you can always get special angles. What if I took, instead of that, 150 plus 45? Now these are both special angles that I can do. So I'll write it as 150 plus 45. And say according to formula, now it's the sum formula, so we'll call this 2a, formula 2a. Cosine of the sum is cosine minus sine. Right? So I just think cosine minus sine. And then if I'm thinking of this is x and this is y, I just put xy. There are other easy ways to figure this in multiple 15 degrees. I don't think you want to do it that way because this to me seems easier. But if you don't like visualization, it might be easier just to recognize there's ways to tell if this is a multiple of 15. How do I know it's a multiple of 15 from algebra instead of visualization and geometry? One way is you've got nice rules. How do you know if it's a multiple of 15, if and only if it's a multiple of 3 and 5, right? It has to be divisible by 3 and 5, the factors of 15. I know this is a multiple of 5, why?
The last digit is 5.
Yeah, if it ends in, it's a multiple of 5, only if it ends in 0 or 5, so it has to end in 0 or 5. And how do I know it's a multiple of 3? That's a little harder. I was gonna say this, there's this trick, if the sum of the digits, a number is divisible by 3, if and only if the sum of its digits is. So you add these up, 1 plus 9 plus 5 is 15, adding's easy. That's a multiple of 3, so 195 is also. Have you ever seen that trick before?
No.
A number is divisible by 3, if and only if the sum of its digits is. So you can add these to 15, so this is how you can do a rapid math calculator. If these add to a multiple of 3, and they do, they add to 15, then the number is divisible by 3. So it's divisible by 3 because these add to a multiple of 3, ends in a 5 or a 0. So now it's a multiple of 15 because it's divisible by both 1 and 3. So you can do it that way if you want. I find this way easier. But all right. So now I can go ahead and break it up into the sum of two special angles. And let's see, if I have an acute angle, 45 degrees, which I'd like to get here, then I go to this standard triangles, root 2 over 2, root 2 over 2. I told you these come up all semester, right? And 1. But for the ones that are not acute angles, you run to the inner circle, right? Which you may have memorized. I showed you that chart you can memorize, right? But I find easier, better than memorization, just figure it out with special triangles. 150 degrees, right, is 30 short of 180. This is how I do it anyway. 150 degrees. And that leaves a 30-degree angle here for the reference angle. Some more room. And now with a 30-degree reference angle, I know the sides on here are 1/2 square root 3 over 2 and 1. And so the cosine of 150 is the x-coordinate minus square root 3 over 2. Sine in here, right, because it's the x-coordinate up to the side of the triangle. Cosine of 45 degrees is adjacent over hypotenuse here is square root 2 over 2. Sine of 150 is the y-coordinate here, plus 1/2. And the sine of 45 degrees, again, here is opposite over hypotenuse is square root 2 over 2. So there, with a little arithmetic, I find I can get the exact value of the cosine. Okay, so what does that come out to do? Well, my top times top over bottom times bottom gives me square root 3 and square root 2 is square root 6, right? And 2 times 2 is 4, and then minus 1 square root 2, so we got minus square root 2 over 4. And this one comes out very similar to the one we just did, just comes out to be minus, if you like, square root 6 plus square root 2 all over 4. It's just the minus, there's a minus on this one also, so there's the exact cosine of 195 degrees done by hand.
Wait a minute, why is there a plus on the answer here?
I'm taking minus the whole thing. It maybe doesn't look like it. Minus is supposed to be out there, so minus the whole thing. I did that so I wouldn't have to put 2 minuses here.
Yeah.
All right. So now, if we can do that for those two trig functions, maybe we can do it for all of them, right? Now, we can derive one formula, maybe just prove it. What if I want the tangent of the sum of two angles? Tangent of x plus y. How do you think I can compute that? Here's another thing to forget on the test. Can we get a sum and difference formula for tangent? Well, again, for the sake of introducing a few useful proofs to help you remember things, I'll say, wait a minute, tangent is sine over cosine, right? And sine and cosine have a formula. This one's sine, cosine, plus cosine sine. And this one's in some trick to help you to memorize it. There's cosine, cosine minus sine, sine. So that would be one formula for the tangent of the sum of two angles. You can memorize that one, but that's too long and cumbersome. So maybe we can reduce it, right? We have trig identities, we can reduce this. If I were to divide top and bottom by cosine x, cosine y, so divide, or let's say multiply top and bottom by 1 over. Multiply top and bottom, so I don't change the quotient, by 1 over cosine x, cosine y. What I'm trying to do is convert these signs into tangents and get rid of these. So on the top, I'll get sine, divide the whole top by cosine, cosine. This is divided by cosine, cosine, and so is this one, right? Cosine x, sine y, cosine x, cosine y. And on the bottom, I divide cosine, cosine by cosine, cosine, I just get 1. And then this one becomes sine, sine over cosine, cosine. So divide top and bottom by the same thing, cosine x, cosine y, and literally multiply by 1 over. Now what do I get? Cosine cancels cosine. This cosine cancels that cosine. I get sine over cosine is tangent. Sine over cosine is tangent. 1 minus sine over cosine is tangent times tangent. Which is a new identity. Tangent of x plus y is tangent plus tangent over 1 minus tangent. Tangent is the way you do that one. I had more trouble with this one when I took it. You don't use it as much for often, as for one thing. You don't use it as often, but also it's a little harder to say it, I think. But that's that one. And similarly, you using the even and odd identities, you replace y by minus y, just like we did for the sign problem. Again, using even and odd identities, the tangent of x minus y, maybe we'll do this proof real quick. I replace all right, y by minus y here. And I also get tangent x plus tangent of minus y over 1 minus tangent x, tangent of minus y, right? Let's replace y with minus y because it works for any angle. But now tangent's odd, so the minus comes out here, and the minus comes out here and cancels this one. And you get tangent minus tangent over 1 plus tangent. So there's a tangent formula for the difference. And then you can combine these because it's easy to remember that way. And we can call these 3a and b. Now we've got the ones for the tangents. You get this formula, tangent of x plus or minus y, finding this tangent plus tangent over 1 minus tangent tangent. And if it's plus here, remember you put plus on top and minus on the bottom. Tangent. And if it's minus up here, you just have to switch it to plus because both these tangents are odds. You can kind of figure it out if you forget. But there's 3a and b. There's a formula for tangent, which is better than just doing sine over cosine. I guess on the test, if you forget, you can still use this one. Just replace the sine and cosine in favor of theirs. But it's nice to have that tangent formula that's faster, right? You don't have to do calculations that one. Let's see if we can compute the tangent of some sort of angle with a multiple of 15 degrees. Let's make this comment first. Now we can apply these three equations, 1AB, 2AB, and 3AB combined, and their reciprocals. The reciprocal identities. Compute any trig function of a multiple of 15 degrees. Exactly. Which again is pi over 12. Radius. Good. Well, let's try an example here. Suppose I wanted to take the tangent of minus 285 degrees. Is that a multiple of 15? Because minus 270 would be a coordinate axis. This is only 15 degrees off, right? So if it's only 15 degrees off a coordinate axis, you're good. So minus 285 is minus 270, minus 15 more, check. It's going to be a multiple of 15. All right, so what do I have to do? I have to write it now as a sum or difference of special angles. And in this case, even though I could write it as tangent of like minus 240, minus 85 and get two negative special angles, I think it's usually easier to use the even and odd identities first. Pull the minus out and call this minus the tangent of plus 285 degrees. Otherwise, I constantly have minus, 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 minus in it. You can do it that way, and I don't mind if you do. It's just easier to make mistakes that way, I think. So I pull the minus out in the beginning and save myself a lot of double minuses later. Now, 285 degrees, I can write as either a sum or a difference of special angles. It'll work both ways. Let's write this as, I don't want to write 270 plus 15 because 15 isn't special, but I could write this as 240 plus 45. And this way I have one acute. I don't have to go to the unit circle. And the other one I can do on, these are both special angles. So I can do this all in one fell swoop. Right? And only one minus out front, so I don't run into so many problems. All right, so this is minus of the whole thing. Tangent plus tangent, the same sign, over 1 minus tangent. That one. And now I just have to put the angles in. 240 in the same order. 240, 45, 240, 45. The angle that's acute, I just run to the special triangle, and for the other one, I'll draw it on the unit circle. So let's see. 45, 45, 90. And again, you can memorize these in your head and figure them out, so you don't have to draw this picture every time if you don't want. Tells me that tangent is this over this is 1, right? Tangent 45 you probably memorized anyway. So this is something plus 1 over 1 minus something times 1. I just have to figure out the other angle. Right? Opposite over adjacent, 45 degrees is 1. Now I have to go to the unit circle to do the other one. So I'll go at 240 degrees. And here's the other advantage. I made it positive, so I go clockwise. That's a little less thinking. Well, let's see. 240 degrees is 30 short of here, or it's 60 past 180. I guess you can call it either way. 180 and 60 makes 240 degrees. And now I can drop the perpendicular here and say, oh, I know the sides. This is square root of 3 over 2, opposite the 60-degree angle. 1/2 over here and 1. So let's see, the tangent would be y over x, if you like, square root 3 over 2 over 1/2, whatever x. Tangent 240 degrees. Square root 3 over 2 over 1/2. Well, it's in the third quadrant, so they're both minus. And then the minuses cancel nicely, right? So it's minus square root 3 over 2 over minus 1/2. Gives us the 2's cancel also, square root 3 of all things. That's not too bad. So all we're just going to replace tangent 240 with square root 3. Now you're going to see the curse of doing these, unfortunately. So this is, if you like, minus 1 plus square root 3 over 1 minus square root. You put this on your answer on the page, that's pretty good because you've got the part, but I'm going to take probably 2 points off for an algebra mistake on this one. At least one, maybe two. Why? Not an algebra mistake, an algebra. You don't want to leave these radicals in the denominator. And unfortunately, it's not so easy as this, right? When I put 1 over square root 2, how did I reduce that? I just multiplied top and bottom by square root 2 to get rid of it and wrote it as square root 2 over 2, right? So this problem, 1 over square root 2, we can easily fix multiply top by square root 3 down here. Anybody remember that from algebra? That's a trickier one, but you need this in higher mathematics. People do it a lot. Because this is actually a mess. This isn't simpler than what I'm going to get at the end if I do reduce it. So you always want to reduce these this kind. This one is simpler maybe this way than this way. So sometimes we leave. Higher mathematics, we always reduce these. And here's what we do. We use conjugates. Sounds like you don't. Anybody remember what to do with this one?
It's like the opposite. It's 1 plus root of 3.
Yeah, there you go. Yeah. 1 plus square root 3 and 1 minus square root 3 are conjugates. And more generally, a plus b square root 3c and a minus b square root c are conjugates. So remember that when you have one of these kinds of things, a plus b square root c or a minus b square root c in the bottom, you multiply top and bottom by the conjugate of the bottom. So I'm going to rewrite this as minus, and the bottom is 1 minus square root 3. So I'm going to multiply the top and the bottom by 1 plus square root 3. And that'll clear out the radicals in the denominator. Any number of the form a plus b square root c multiplied by its conjugate, the square roots cancel. Can you see it already? If you FOIL here on the bottom, all right, 1 times 1 is 1 plus square root 3. First outside plus square root 3. Inside minus square root 3. Minus square root 3 times minus square root 3 is minus 3. Right? And the square roots cancel. It always works with conjugates. On the top, not so lucky. We've got 1 plus square root 3 squared. So I can multiply that out and write that by FOIL. 1 times 1 is 1. Plus square root 3 plus square root 3 is plus 2 square root 3. And then plus square root 3 times square root 3 is 3. So this is the outside and the inside combined here. And now 1 minus 3 on the bottom is negative 2. On the top, 1 plus 3 is 4. And I got 2 square root 3. So I get this, and then I got to carry my minus out here for the whole thing. Oh, nicely, this minus cancels this minus. Make sure you divide both of these, right? 4 over 2 is 2. 2 square root 3 over 2, the 2's cancel, and you get square root 3. This is a whole lot simpler to write than this, right? So this is going to be wrong. You want to simplify it to 2 plus square root 3. Now, there's not even a quotient here anymore. Actually, you'll find in a lot of these problems, this is the curse I talked about, is that the algebra is actually harder than the trigonometry. So you got all these deductions to make. All right, that one look okay? We're gonna move on then. I said back there that you can do any trig function of a multiple of 15 degrees by using these together with the reciprocals, right? Also, we said we can do this in radians too. So for instance, suppose I wanted to compute the secant of 5 pi over 12. Is that an angle I can do exactly by hand? These are easy to tell. Right? If it's not already obviously a special angle, you just look, is it a multiple pi over 12? Sure it is, it's 5 pi over 12, right? So I just say 5 pi over 12, 5 is a multiple of pi over 12, so I'm good. But to do the other three things, what we do is we don't memorize their formulas. Who wants to do more memorization than you need? You just always use the reciprocal. You say this is 1 over the cosine of 5 pi over 12. And use the cosine identity. So that's the trick. The last three, cotangent, secant, and cosecant, you just take the reciprocal of the three we already did. Don't forget to mark this. Maybe I just erased it. Oh, no, no. This is 3AB here. Better not. I referred to it. All right. So now cosine of an angle, again, you write it as cosine, cosine, minus sine, sine. Maybe I better first write this as a sum of special angles. So here's the harder part with radians, is writing it as a sum of special angles. How do I write 5 pi over 12 as a sum of special angles? Well, special angles are multiples of pi over 6 and pi over 4, so I've got to do that. 5 pi over 12. I know it'll work. I just have to figure out the angles. It's harder than degree. Well, what can I do? I could call this 3 pi over 12 plus 2 pi over 12, right? That makes 5 pi over 12. Then I just have to figure out if those are special angles. If 3 pi over 12 is special angle, well, 3/12 is 1/4, so it's pi over 4. That's special, right? It's 45 degrees. 2 pi over 12 is pi over 6. That's 30 degrees. Hey, there we go. So there's a way I can write it as sum or difference. Write it as so many 12s plus so many 12s and see if it reduces to special angles. So this is actually going to be cosine of pi over 4 plus pi over 6, the sum of two special angles. Or if you get flustered on the test, you can always convert it to degrees, and that works. I'll accept it if you convert it to degrees and do it that way, all right? It's just in the long run, you really prefer to do it this way, so you don't have to convert. But on the test, do what it takes to get it done, even if it's longer. All right. So now cosine of the sum of two angles is cosine, cosine minus sine, sine, right? Plus with minus on cosine. And I put the angles in order. Cosine pi over 4, cosine pi over 6, minus sine pi over 4, sine pi over 6. And we only have to memorize three identities for the sum of angles formulas, even though there's 6 trig functions. Let's see. Once again, we'll draw the triangle. And fortunately, since we've got two acute angles, we don't have to draw the unit circle. So here's pi over 6 up on the corner here. It goes opposite 1/2. And then the square root 3 over 2 goes here. And there's 1. And then the 45, 45, 90 or pi over 4, pi over 4, pi over 2 triangle. We'll have square root 2 over 2, square root 2 over 2, 1. So let's see, the cosine pi over 4, we maybe memorize this. This is adjacent over hypotenuse, square root 2 over 2. Cosine of pi over 6, this one is adjacent over hypotenuse, is square root 3 over 2. And then we subtract sine pi over 4 is square root 2 over 2 off the triangle. And sine pi over 6 is opposite of hypotenuse is 1/2. So there's what we have for the secant. Is 1 over, multiply these, top times top over bottom times bottom, is the square root 6 over 4. Minus top times top over bottom is square root 2 over 4. All right, we can combine them as before, get a common denominator, square root 6 minus square root 2 all over 4. And now this becomes nicely 4. Right, the reciprocal of any quotient, let's just turn it upside down, 4 over square root 6 minus square root 2. Well, we can do this in 2 steps with the things we already know. We can multiply top and bottom by square root 2, for instance, and write this as square root 12 minus 2, and write it as a minus b square root c. But what's easier in these cases than converting it to a minus b square root c and then doing that is just say we'll multiply top and bottom by square root 6 plus square root 2. So when we have even square root minus square root, we'll do the same thing. We'll say that the conjugate is this, even though this isn't its common notation there. Multiply top and bottom by, change the minus to a plus. Square root 6 minus square root 2 times square root 6 plus square root 2 is a pseudo conjugate, I guess you'd call it, at the bottom. And there we've got it. This will get rid of the square roots in the denominator. See. So let's see, on the top, I could write this, I'll just leave it alone for now because I might get something to cancel. It's nice to have it factored sometimes. 4 times square root 6 plus square root 2. Did I not tell you to learn some algebra in this class? I'm gonna force you, unfortunately. Root 6 times root 6 is 6, right? Minus, plus square root 6 times square root 2 is plus square root 12. And then minus square root 6 square root 2 is minus square root 12. Minus square root 2 minus square root 2 is minus 2. And sure enough, these things cancel this time also. We've got 4 times root 6 plus root 2. All over 6 minus 2 is 4. Oh, good thing I didn't multiply that 4 and it turns out it cancels. This comes out to be square root 6 plus square root 2. How about that? There's the exact value of the secant. Of 5, 5 over 12. Okay. So again, don't leave it like this, right? This might think you're done, but it's probably 2 points off because it's a lot of algebra. You can get rid of the quotient entirely. It's probably square root 6 plus square root 2. Okay. So that's doing these special angles, but we can do more with these actually than just do some trig functions of new angles. What did we say about all these identities last time? Identities can be used to simplify trig expressions and to prove new identities, right? So we're also going to do that. Furthermore, 1, 2, 3 can be added to our previous identities. Allow further simplification of trig expressions, because we now got more identities to throw at it. And verification of non-tabled new identities. Well, I remember the rules of thumb for doing these things. You don't have to do this. It's just a nice organized way that works quickly. And remember how we simplified? What we did was I'm going to leave a little space here. We used algebra. I'll do one last time. To eliminate, to reduce algebraically. We could do things like eliminate compound quotients, right? Quotient of quotients, we write top times bottom over middle. We could combine common denominators. So sometimes we'll get common denominators, combine them, and then eliminate the compound process. But this is how you simplify things in algebra. We canceled common factors. That's mostly the quotient theorems that we're interested in from algebra. But sometimes you use something else, so I'll say etc. Those are the main things you do. Then you said, well, once you've gotten rid of all the things algebraically, you go to trig identities. You see sine squared plus cosine squared, you replace it with 1, right? You don't leave it sitting over the mess. And then finally, if you're stuck, you can rewrite using sine and cosine only. That makes it easier. Remember those rules? It's been a long time. I had to recopy these. Sine and cosine only. Now, especially if you've got more than 2 trig functions, I said, if you can reduce it to 2 trig functions, that almost makes it easier. Almost always makes it easier. And then you iterate on this, right? So you repeat this part. Well, now I'm going to add one more rule to that, rule 0, because you don't repeat this one, actually. You get one angle. When you have cosine 2 theta in there and sine 3 theta in there, you just can't reduce it until you first get it down to one angle. How do you get it to one angle? You can use these sum and difference identities to reduce it something. So I'll say these are the 4 steps that you have for this one. There's one more rule for the simplification. And then how do you verify identities? Remember what that was? Use the same 3 steps over and over, but also work both ends towards the middle. So you simplify from both sides. It's an easy thing to verify identities. Again, you don't have to do this. Sometimes I like to write a sequence of equivalent statements until I get to the identity. Student, but I found in the long run, it's easier just to work both ends. It's not as much writing. So also work from both ends to verify identities. To a middle meeting. Both ends of the equal sign. So let's see if we can do some of these things. So here's a simple example out of the homework. Rewrite in terms of sine and cosine of just one angle, the first step here, step 0. This will be the easy problems, then we'll build. That's right. Suppose I gave you the cosine of pi plus 2 pi over 3. This is problem 2b in your homework. All right, that's a mess. I don't like cosine of a sum of angles. How am I going to write it in terms of sine, cosine of sine, cosine of one angle only? I meant to say. I think I said that and then wrote it wrong. Of one angle each. What you can do to simplify this is say, oh, by the sum of angles formula, so I just call this x and this y. This is cosine, cosine minus sine, sine by 2a. Or I put in x, y, x, y. But now I know what cosine and sine of pi are, right, off the unit circle. Here's the angle pi, the straight angle. Point out there is minus 1, 0. That's the cosine and the sine of pi. So the cosine of pi is -1, the sine of pi is 0. So this is -1 times cosine 2 pi over 3 minus 0 times something is 0, right? But I didn't need to compute this. What's the cosine of 2 pi over 3? Well, I can figure that out in a circle. Drop the perpendicular, and I say, well, that's 2 pi over 3, and it's pi in the whole thing. This must be pi over 3 is the special angle. I know what that is. That's 60 degrees, so this side is a half. Cosine is -1/2, right? So this is -1, -1/2. Where's this wrong? Now let's put the x plus pi. I misread that. Apologies. I was doing something with that. Should have been x plus 2 pi over 3. What was my problem? Otherwise, you just rewrite that 5 pi over 3. X plus 2 pi over 3. I get for not putting my glasses in. It's cosine, cosine minus sine, sine with x in here. And now, I don't need pi, do I? I just need 2 pi over 3. So I've got cosine x. Cosine of 2 pi over 3 is -1/2. Sine of 2 pi over 3 is the y coordinate plus square root 3 over 2 off the unit circle. Oops. And there's what I've got. All right, and so I can rewrite this as -1/2 cosine x minus square root 3 over 2 sine x. And now I've written in terms of sine and cosine of the angle x only, which can be convenient if I'm measuring that. I don't have to add it and take something. So sometimes it's better in this, sometimes it's better in that, but that's how you rewrite that. Okay. Here's another one. Hey, let's just leave that example. I want to do one of these. Suppose I said simplify. How can I simplify? This would be 3a secant of pi over 2 minus theta. How can I write that simpler? This is sort of the same thing. Again, there is a sum and difference angle formula for secant, right? There, you can write one down, but it gets too much to memorize. This isn't used that often. So usually what we do is we just take the reciprocal and say it's 1 over the cosine of the difference. Well, if I think of this as x and this is y, what's subtracted here? Right? Cosine of the difference is cosine, cosine plus sine, sine. Right? Minus goes with plus on cosine. And I just put in what x and y are. It's cosine pi over 2, cosine theta, plus sine pi over 2, sine theta. There it is. And now cosine pi over 2, if you go to the unit circle, and sine pi over 2, they're easy, right? You get 0, 1, so the cosine is 0 and the sine is 1, and the cosine pi over 2 falls out. That's 0, right? And the sine pi over 2 is 1, so in some sense that falls out. And look how nicely this simplifies when you get in terms of one angle. It's 1 over 0 plus sine theta. Oh, this is just the cosecant of theta. oh yeah, this was the cofunction identity. So I just reproved the cofunction identity, but sometimes these simplify, like if you got secant pi minus theta or that kind of thing, then it can simplify it even though you didn't have that identity before. But this verifies the cosecant identity. And if you see secant 3 pi over 2 minus theta, it's nice to write it in terms of cosecant instead of making this, leaving this in terms of two angles. So they're simplifying. You can get one angle and make these things a little easier sometimes. Now, we can also evaluate some other things. What was a given? Actually, let's use a verify. I wanted to finish that one up. Verify these identities. That tangent of x plus pi over 4 is actually equal to tangent of x plus 1 over 1 minus tangent x. How about that? Is that true? Hard to tell, right? You can write an infinite number of equations and say maybe that's an identity, but isn't one really true for all angles x for which both sides are defined, so we call it an identity. What you do is you follow the rules of thumb, right? And the first, and use the verify process I recommend, and write equals, 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 and see if you can make the two ends meet, right? Can I make those meet? The first thing you do is you try and get rid of, try and get just one angle. I can get some room there, right? Get one angle for each thing. So you get rid of this using the sum of angles formula and say tangent x plus y is tangent plus tangent over 1 minus tangent tangent. Right? So there it is. I'll get rid of, this is by rule 0. Now maybe I can make these ends meet now that it's just tangent of x. And now tangent pi over 4 I'm using the unit circle. Remember what tangent pi over 4 is? I memorized it. Right? Pi over 4 is this 45-degree angle. Actually, let's do the triangle. I said do that. If I put pi over 4 here, 45 degrees, it's root 2 over 2, root 2 over 2, 1. So the tangent is opposite of adjacent is 1. So this one can be replaced by 1, and so can this one. So this is just tangent x plus 1 over 1 minus tangent x times 1. Oh, there it is, right? I can go either direction. So this one I could just go forward and find it. But the idea is you have to get that sum of angles out of there. You want to get each of these at trig function of one angle, one number. So this is actually an identity. Nobody wants to memorize this. It's just when you need it, you figure it out if it's really true from the ones you memorize. Okay, so that was the points on those. We're going to do a whole lot more of those in the future. But for now, we'll say these are some kind of verifications you do for simple cases. And then finally, this is like piano practice. This isn't a real problem, but it's to work your fingers, right? I had to take piano lessons and simply down by somebody maybe great pianists, but they made me play things da 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 da. Who wants to hear that song, right? But it's supposed to get your fingers going right. So this is your piano practice for this one. It's supposed to get you learning this stuff, even though it's kind of useless problems. Given, and this comes out of every trig book you'll see. It's a real good way to do mental exercise. Given that the sine of alpha is 2/3, and cosine b is 1/4, I'm going to put beta equals 1/4 minus 1/4, sorry. with A and B both in the interval pi over 2 to 5. Find sine of A plus B and cosine A minus B. Or alpha plus beta. Put an alpha and beta again, alpha beta. What is the sine of alpha plus beta if I know these? All right. Well, what does this mean first? Alpha beta in this interval. In this interval notation. Square bracket means include it. Round bracket means don't include it, so it looks like this. And that is that both alpha and beta are between 90 degrees and 180 degrees, not equal to 180. So it means quadrant 2, that's all it means. So they're both, these are both in quadrant 2. All right, so what do? To find sine alpha plus beta, I go to my identity. This is sine, cosine, plus cosine sine phi 1a. That's the very first one, sine of the sum of two angles. And alpha, beta, the same order. Just putting alpha instead of x, beta instead of 1. And now, how can I get all these? Well, I've got cosine beta is minus a 4. And then sine alpha is 2/3. But how do I get these other two? How about that? Well, I touched that principle. If you know one trig function in a quadrant, you know them all, right? So here I know a trig function, sine alpha is 2/3. I know alpha is in quadrant 2. I can find all 6 trig functions. I can find cosine alpha. I'll take cosine alpha over here and say cosine alpha is, there's lots of ways to compute this. I like plus or minus square root 1 minus sine squared, right? And it's in quadrant 2 where cosine is negative. So I have minus the square root of 1 minus, let's see, sine was 2/3. So minus 2/3 squared was minus the square root of 1 minus 4/9. Remember how to reduce these? Put them over a common denominator. Square root 9/9 minus 4/9 is minus the square root of 5/9, which then reduces to minus square root 5/3. Keep your algebra teacher happy. So I can replace cosine alpha with minus square root 5/3. What about sine beta? Down on the side somewhere. Let's see, if I follow the same process, if I have sine and find cosine, cosine beta is plus or minus square root 1 minus, I'm sorry, sine beta is plus or minus square root 1 minus cosine squared. There's, well, let's see, it's in quadrant 2, sine is positive, so I'll take the positive here. Plus for sine though. It is plus the square root of 1 minus cosine was minus a 4th. Squared. Well, you square a negative and it becomes positive. So this is square root 1 minus a 16th. And once again, let me get rid of this. It's in the way. Square root of 16/16 minus 1/16, getting a common denominator for adding and subtracting fractions. The square root of 16 minus 1 is 15. 16, oh, square root of 15/4 if I reduce that, right? So this one I'll have to write as square root 15 over 4. And now I've got it, right? Here's the exact value of the sine of alpha plus beta. I don't know what alpha and beta are. I just know what the sine of alpha and the cosine of beta are. So minus 2/12, right? Top times top over bottom times bottom. Minus square root 15 times square root 5 is minus square root 75. 4 over 12. And so I've got minus 2 plus square root 75 all over 12. Now that's the correct answer, but there's still a point off. So once again, if you leave it here, there's a couple points off. If you reduce it to here, there's still a point off, right? Why is there still a point off? Yeah, square root 75, I noticed, can be rewritten as square root of 3 times 25 is 5 square root of 3. So you want to do that, rewrite this as 2 plus 5, minus up front. Minus 2 plus square root of 5 all over 3. So lots of hard algebra this stuff. I don't know why you ever studied that, I suppose. Let's see, do this kind of stuff. You don't want to leave it like that, right? That's a mess. Okay, that's that section. There's a nice stopping point there. You want to do section 7.2, 1 through 7. But you may want to wait until after you study for the quiz this Friday. This is not for the quiz, this stuff. Thursday. This won't be on the quiz. But when you get a chance to do this, if you study for the quiz.
Can you remind me what sections of the quiz again?
Yeah, yeah, 6.3, I just said the first 9 problems. And then all of them. So the exam will wait for Thursday, this will figure out. Good.